Okay, AP Calculus BC, Unit 3, Day 2, Mean Value Theorem for derivatives specifically. So, there are some requirements to use the mean value theorem. Function needs to be continuous, just like extreme value theorem requires, and on a closed interval, just like extreme value theorem, same. And is differentiable. That's not a requirement for mean value theorem. And this is really for the derivatives. And it's differential on the open interval because we're concerned with the closed interval, but we generally don't want to talk about derivatives at the edges because they're two-sided issues. And we're clearly at these edges, not looking beyond those. So we're not going to look at derivatives at the edges, but up until. And what the mean value theorem guarantees is there's at least one point, at least one, C, at least one could have more than one. Okay. But at least one between the endpoints where the actual derivative equals the average derivative. Okay. The actual derivative equals the average derivative. Now, the average derivative, it's kind of a basic idea that I feel like can seem pretty intuitive and not a formula to memorize. If you have a function and you say, well, I want the average of all the slopes between A and B. Well, there's all these infinite little tangent lines. And what happens is it really is just the slope of the secant line connecting the endpoints. You just do slope between the edges and you get the average slope. So the actual slope equals the average slope or the average rate of change. And the way we calculate that is we say, okay, well, if this is A, this would be A f of A as an ordered pair, and this would be B f of B. And we just do rise over run. F of B minus F of A over B minus A. So that's how we find the average slope, is we just take the slope between the endpoints. That is not a formula to memorize. It's a simple idea to remember. Okay, and hopefully it feels like, oh yeah, the average of all these different slopes would end up just being that slope. Now in my picture, you'll see that the actual slope here is equal to that, and here. So those would be C values, different C values, but mean value theorem guarantees that you at least get one of those if the function is differentiable on the open interval. So, okay. Now, don't confuse this with mean value theorem. Other versions of the mean value theorem that we've learned, we'll talk about those at another time. We're not going to deal with them right now, but this is the actual. This is if you wanted, if you have a function and you want the mean value of the actual function, well, that would be like the average y value. And the way we calculate that is we say, okay, well, if we take the area underneath and we smooth it out, it's going to be a rectangle with the same area. And we want, that smoothed out version of the curve is the average height, the average function. And then this is the base. And so we say, okay, well, let's find the area of the rectangle, which is the area under the curve, and divide it by the base to get the height. So, but that's just another version. We're not going to deal with this right now. We're just going to do the derivative one. So here's a few examples. And so here's a function. Now, one of the things you might want to make sure you check is that you're actually allowed to use mean value theorem before you start making conclusions based off it. So is it continuous on a closed interval? Yes. You can look at this, it's a cubic, that's a continuous function on a closed intervals right here, so that's good. Is it differentiable? Well, we'll have to look at the derivative, which we're going to find anyways. We're going to need it. So the derivative is 3x squared, which exists everywhere, which is continuous itself, which means the original function is differentiable at least on the open interval. Okay. So that's good to just check. So what we're going to do now is we're going to find the average slope by doing f of 4 minus f of negative 1 over 4 minus negative 1. I find it helpful to just write this down. You plug 4 in here, you get 64 plus 5 is 69. You plug negative 1 in, you get negative 1 plus 5 is positive 4. On the bottom, we have this. You get 65 over 5 equals 13. And that's your average slope, which you might be asked for. But a lot of times they ask you, well, find the C values where the actual rate equals the average rate. So they might not ask you to find the average slope, average derivative, average rate, but you're going to need it for the next part. So now we're going to take this derivative and set the actual derivative at, we usually call it like a C value, but we just put x equal to the average derivative. So 3x squared equals 13. So then we could solve for x. Take the square root of both sides, plus or minus. I need to see that in your work. So these are the C values. So we could do, we could simplify this plus or minus the square root of 13 over the square root of 3. Then you could rationalize the denominator. Multiply top and bottom by square root of 3. But your final answer, we got to make sure that whatever answers we pick are going to be between the endpoints. Now, square root of 39 is about 6. It's between 36 and 49. So it's probably like 6.3 over 3 is 2.1. Is that between negative 1 and 4? Yep. How about the negative version? Nope. So we're only going to take the positive answer for our C value, which as a decimal, if you use your calculator, is that. Okay. Now I want to see the work. In your work, you might find extra C values, but then decide to not use them. Now, just to give you a quick idea what's going on here, this is a picture of the graph. Okay. And so we have this, it's a cubic. And then we're saying, well, we just want to look from negative 1 to positive 4. And so these are the endpoints that we're using right here, right? And so the line connecting them is your average slope. Actually, yeah. So anyways, I think I might have messed that up, but okay. Okay, so write the equation for the secant line. That's that line that, so we already found the slope of it. The slope is the average derivative, which we said was 13. And we need a point. So either endpoint will work. So you could do y minus 4 equals 13 times x minus negative 1. So y minus 4 equals 13, x plus 1. That's one answer. I'd leave it in point slope form unless there's a reason. Or you could do y minus 69 equals 13 times x minus 4. That's fine also. It actually ends up being the same line if you change from slope and slope form. Write the equation for the tangent line, the actual tangent line that's parallel to the secant line. So this is that C value. So we have the slope. The slope is the same slope. Okay, but we need a point, and we have the x value. We have x equals square root of 39 over 3. So we got to find the y value. So we got to plug, we got to plug this in. And so find the, the y value at that C value. This is a tiny bit. You got to plug it back in the original equation. Okay, now I'm going to say, okay, well, this is a square root. So if you square it, you get 39, and then you're going to still have a square root of 39 left over 27 plus 5. I mean, we could just go with that. we could reduce this to 13 over 9. So we could say 13 square root of 39 over 9 plus 5. We could combine them into a single fraction if you want, not required. Okay, but then we could write the equation. We could do y minus, let's just go with this, 13 root 39 over 9, and then we got to distribute the subtraction of the 5 equals the slope with x minus the x value. So something like this. It's a little messy. But that's the slope of the parallel line where that special thing happens, where the actual slope equals the average slope. Okay, got a couple more examples on the back. So here's a function. Let's check the conditions. This is like the Siegel function. Kind of looks like this, and then it gets shifted up. So it is continuous on the closed interval. Okay. But it is not differentiable. Okay. So, and you could verify that through the work. G prime of x equals 2/3 x to the negative 1/3, which is the same thing as 2 over 3 cube root of x. And if you set this equal to, what happens is x cannot equal 0. Otherwise, G prime is undefined because you get that sharp corner. Okay, so that makes sense. By the way, that this graph has been shifted up 5 units. So now we could see, I think you get some infinite slopes here. Now it might kind of work out to find the average slope, but we can't get the guarantee for sure because, and I'll show you on the graph. So the graph, so we have this cusp here. If we were to make a little nicer graph of this from -1 to 8, and you plug -1 in, cube root of -1 is -1 squared is +1. Gives you 6. And then at 0, the interesting thing happens is that's where you get the cusp. So you plug 8 in, cube root of 8 is 2, squared is 4, plus 5 is 9. 7, 8, 9. So that points up here. And the graph is this like Siegel graph, and it kind of looks like this. Now, if you connect these, that's the secant line that you're going to get the average slope from. But there's these infinite slopes. I think, because it's symmetric, it's going to end up working out, I think, this time. And you just got to be careful. But this is not differentiable on the open interval -1 to 8. So sometimes graphs have indifferentiable points, but if they're if they're not between the endpoints you're looking at, then whatever, that's fine. You can do the work. But this is right in the middle of what we're concerned with. Anyways, I mean, we could do G prime average equals G8 minus G -1 over 8 minus -1. This is dangerous. I think on this problem, it actually kind of works out. Cube root of 8 is 2, square root is 4, plus 5 is 9, -1. Cube root is -1, square root is 1, plus 5 is 6. And you get 3/9 or 1/3. So, I mean, this is a little sketchy. Now, here's the deal. You could just look at this picture. Is there an actual slope that ever equals this average slope? I don't think so. And that's because of this cusp. So that whole thing, and you could try and solve for it. So you could get an answer. You could do G average, x equals 2 over 3 cube root of x, and set it equal to the average slope. We could multiply 3 by both sides. We could flip both sides over. We could multiply by 2, we could then cube both sides, and then we could get a value c equals 8. And you might think, oh, that's fine. Look, we got one. Now, there's a couple issues with this. One, it's just not true. 2, it's on the edge, so we would throw it out anyways. But, anyways. Now, if we change the problem a little bit, we said, okay, let's do the same one, but let's do 0 to 8 instead. Well, that would be on a section of the graph that was continuous and differentiable on the open interval. So it's continuous on the closed interval. Okay. And it's differentiable on the open interval. So this one, we can do it. Okay. So, the derivative is the same thing. And x can't be 0. G prime is undefined there, but that's fine because we don't care what the derivative is at 0 because it's on the edge. But on this one, we could we find the average slope. G prime average would be G8 minus G0 over 8 minus 0. And that would be that would be 9 minus 5 over 8 minus 0. It's 4 over 8 equals 1/2. So this is your G prime average. And then you could set G prime of x, safely set it to this value. Now, just like I said, sometimes you set it and you get some answer. That doesn't mean it was good, though. I would flip both sides. And I would multiply by 2. And I would divide by 3. And I would cube both sides. And I would get x equals 64 over 27. And that is your C value. And make sure that is 2 and 10/27. Is that between the endpoint 0 and 8? It is, so that's good. But we expect to get at least one on them. Okay, next one is a piecewise function. And so I think it's helpful, at least right now, to just get a sketch of it. So let's take a quick sketch of this. So from -1 to 1, it's this other function. So let's just sketchy these. So this is a cubic moved up 3 units. So you plug 0 in, you get 3. Plug 1 in, you get 4. Plug -1 in, you get 2. Plug 2 in, you get 8 plus 3 is way up there. So it kind of looks like this. Okay, and then the other one's a parabola. It's been moved up 1, over 1, up 2, over 2, up 4. Both sides, over 2, up 4. So it's kind of like this. Okay, now from -1 to 1, it's the cubic. Solid dots, it says. Well, no, okay, never mind. This is the endpoints for the whole thing. This is where we're going to try and find f prime average for. So for 1 to the left, it's the cubic with an open dot. Okay, and then at 1, it's a solid dot, and it follows a parabola. Okay, now that's not a continuous function or differentiable on a whole, but if we're only looking at -1 to 1, then we're looking at this function from here to here. Now, technically at 1, it's right here. So you're not going to do that. You're going to do this. And that's not going to make sense. So we're not going to be able to use mean value theorem. Now, if you didn't have a picture, you could confirm if it was continuous by doing the one-sided limits at the transition point. So you could say, well, what is approaching on the left side of 1? And you would say, well, we're going to use this guy, and you're going to get 4. And then you say, well, what's the limit on the right side? So here's the work you could show to show that there's some kind of jump or something there. Now, from the right side, we're supposed to use this other function, x squared plus 1, and that gives you 2, and they're not equal, so it is not continuous. So we just can't even do it, okay? So on your homework, you might get some problems where you need to just say, hey, I can't do mean value theorem. It's not, and support your decision. Tell me why, maybe have some work. It's not continuous, therefore it's not differentiable either, which doesn't even matter. Okay. So we can't use mean value theorem. Okay. Can't even get the average slope. Okay. Another quick problem. Let's say you travel 300 miles in 10 hours. You could find your average speed, which is like an average derivative, right? How far did you go? Change in y over how long has been, change in x, and you get 30 miles per hour. So then by mean value theorem, at least once you were going 30 miles an hour, right? So, all right, try the homework. I think let's just do the odds. Let's just make it a little small. Why not? There you go. Happy, whatever.